So we've got this handout, creating frequency distributions. There's another video where we talk about categorical frequency distributions. Categorical data is like this. It's not numbers. It's different categories of things, and then when we count them, we get some numbers. But our things that we're counting are not numbers. So for the example I'd like to look at here, this is from your text, page 316. This is the record high temperature in each state. If we were to treat this like categorical data, we would count all of the ones that said 112. And that would be one category, and we put how many of those there are. How many of them are 100? We count all the 100s. That's going to be kind of ridiculous. Instead, we're going to group close numbers together.
Hey, Mommy, can you eat my cheese?
We're going to call these grouped sections of numbers the classes. Now, some things to think about when we're making classes. We don't want too few. If we put all of these, let's see, it looks like our smallest, I marked that. Our smallest one is 100. If you just go through and find the smallest. And then our biggest is 134. If we were to just have two classes, put the bottom half in one and the top half in the other, that's not really telling us that much information. It's not going to be that helpful. We don't want too many classes either, because then it's kind of overwhelming. If we have just, this huge list, and it's like, how many of them are between 100 and 101, and 102 and 103, and like, there's going to be so many of them. That's not going to communicate well either. So we probably want somewhere between like 5 to 8, maybe 10. We want to have enough that it's meaningful and few enough that it's meaningful. The second thing we want to think about is that each class needs to be the same size. If our first class is like 101 to 103, and we've got, however many of those, and then the next class was like 104 to 120, that's a lot of different degrees. And when you look at those bars and how many there are, the fact that you are casting such a wider net for that second class is going to make your graph not be clear. It'll be misleading. We don't want that. So, long story short, make each class be the same size. Then we also want to make sure we're including all of our data. If you start with a class, if I started counting how many there were at 105, then I'm not including Alaska. So make sure that you start below or at your smallest. You go all the way up to swallow up your biggest. You want to have your categories, your classes to be the same size. And then it's nice, if possible, if they can be pretty numbers. So we're used to counting by 10s, counting by 5s, counting by 3s we're comfortable with. Try to start on numbers that kind of are pretty, if you can. So I know I'm going from 100 to 134. 100 is a nice number to start on. Instead of starting on 99, I might just start on 100. And if I were to count by 5s, I'd have a class that's starting at 100, 105. Okay, this is what I've got. Now, will this include everything? My smallest is 100, so it fits in there. And then my biggest is 134. Well, I'm counting by 5, so yeah, that'll fit in that last one. This is a nice arrangement. If I were counting by tens, I would have too few categories. I'd have one starting at 100, 110, 120, 130. That's just be nice to have more. If I were counting by, say, twos, I'd have way too many. This is good. Now let's talk about like our end here. Another rule when we're making a grouped frequency distribution is that we don't want to let anything fall through the cracks. Like if I were to say, okay, I'm going to have this go from 100 to 104, and because the next one starts at 105. If I have a piece of data that is 104.7, it falls through the cracks. 104.7 is bigger than 104, but smaller than 105. Doesn't fit in. Now, all of this data, these are all rounded to the nearest whole number. So going to 100 to 104, that's just fine. Nothing, I've got no decimals. So that'll work out great. 100 to 104, I can do 105 to 109, etc. One way to combat that some grouped frequency distributions will do, is to actually use your boundary number twice. So 100 to 105 and then 105 to 110. But the issue with that is, what do you do for that boundary number? If it's 105, where do you put it? Do you put it with this one or this one? So you've just got to choose and by convention say, all right, anything that's on the boundary number is going to go up. So if 105 would go in this class. If I happen to have 110, it would go in this class. Some frequency distributions that you might see might be like that. If they don't tell you what the convention is, you could probably assume that it's the beginning number that's significant. So it's 100 and everything all the way up to that next number that starts the new one. So now I'm just going to go through, I'm going to put in my end numbers. I'd like to point out one more thing. It's just a coincidence that my lowest number is a boundary number and my biggest number is a boundary number. It's okay if your boundary number is a little bit bigger. Like if my biggest number was 132 instead of 134, I would still want this to go all the way up to 134 because I want every single class to be the same size. Or if my smallest number was 103, probably still have a class that started at 100 and went to 104 because 100 is a pretty number to start on as opposed to starting at 103 and counting by fives. It's okay if your classes kind of overlap. As long as they swallow up all your data, that's good. Okay, so I've counted up the frequency. So the biggest mistake people make on problems like this is they just skip one or they accidentally count it twice. So I would recommend, if you possibly can, get away with writing on your data. Just mark it off as you're counting it so you don't skip one. And then maybe once you've got all your frequencies in there, add them up and see if the number matches the total number you had in your chart. Just to kind of double check that you didn't double count something or miss something. I just went through and counted how many of them fit in this group, how many of them fit in this group. And that's what I've got. It is so easy to make an error on miscounting that the textbook authors actually did that. Okay, so the textbook authors, in section 4.2, on page 334, they recreate this frequency distribution and they have some of the numbers off. So I would recommend, if you're doing number 1 on page 334, just go ahead and use the different one that they have. But you can feel superior knowing they made an error. I wouldn't make that error, of course. You have permission to feel superior over these textbook authors and their error. So if you have group frequency or grouped data like this, common type of graph for this kind of data would be a histogram. A histogram is a lot like a bar graph, except your bars are touching each other because they're not just categories that can be interchanged and don't particularly have an order. These do have an order. This is the smallest. These are the coolest temperatures, then the next coolest temperatures, and the next. The order matters, and they're right up against each other because the boundary numbers are like a boundary of both the boundary numbers of the boundary of this and of this. So the bars touch each other on a histogram. The other type of graph you might commonly see with something like this is a frequency polygon, which is a lot like a histogram. So whoop, that's what a histogram looks like. A frequency polygon, instead of having the bars, has a dot where the tip of the bar would be. And then a line connects them. Then the other added thing is that they connect to the ground on the outside. We'll talk about that when we're specifically talking about that. But those are the two big types of graphs that we'll see with this kind of data.